This lesson is going to look at using redox reactions to do stoichiometry. So it's really just combining two things we've already done. One is writing a balanced redox reaction, and the other is stoichiometry. Now why this is important is because redox reactions are often used in analytical chemistry because we have, in many cases, a very nice signal to that endpoint in that things with different oxidizing states have different colors. So two examples that would be like that are permanganate ions. They're that bright purple, so when they react we lose that bright purple color. Depending on which kind of reaction, what they end up going to. And the dichromate ions, we have that kind of orangey color, and again, depending on which state of chromate they go to, what color they change to. So they're both strong oxidizing agents, right? If you look on our chart, they're way high up there. And they both undergo a visible color change. So they make good indicators as well as reactants, right? They act as both. So our first example, we've got iron 2 ore, and it's being titrated to determine the concentration of the iron ions, right? In other words, how much iron is in this ore is what you'd be trying to figure out with this. So the first step on these sorts of questions is to first balance using some method. So I mostly do these ones with half reaction method because most people are more comfortable with the half reaction method. And so on these we have to identify again what is changing. So we have that cerium, I should say, going from +4 to +3. So we know that's happening. So how is it getting there from +4 to +3? We're going to have to figure out where our electrons go. So that one is gaining electrons. It's the reduction side of things. And it gains 1 electron to go from +4 to +3. The other side of this, we know we're starting out with iron 2, but what's happening to that iron 2? So we know our reactant, and we've got to stop and think about, well, what's going to happen? Well, if the other side is being reduced, the iron has to be oxidized. So it has to be losing electrons, and iron does have 2 possible oxidation states, so it's going to go up to that +3 by losing an electron. And we can see that that's already balanced because we have 1 electron and 1 electron. So this one happens to be a 1-to-1 all the way across reaction. So that part is our balancing. In stoichiometry questions, our first step is always to write our balanced equation. So all of this is technically one step of our stoichiometry. What do we do after that in stoichiometry? So step 1, balance the equation. Step 2, go to moles. Step 3, use our mole ratio to get to our desired substance. And step 4, use whatever means we need to get to our desired units. So maybe we already are there. Step 4 isn't always needed, but that's our 4 stoichiometry steps. So let's identify what we know in this question. We have 25 milliliters of this iron sample, so that's going to be 25 mils on our iron +2. And we know both the concentration and the quantity of the cerium solution. So we have that. So which one do we know enough about to find our moles? Well, we have concentration and volume, so we can take this one to moles. Then we can use our mole ratio. You might be tempted on a question like this to use C1V1 equals C2V2. And coincidentally, when it's a 1-to-1 reaction, it will work, but we don't want to use that because it won't work if it's anything other than a 1-to-1 reaction. So be careful on that. So after we have volume times concentration to get us to moles, we can then use our mole ratio. We want to end up at concentration of iron, so our mole ratio is going to be with iron. And then we want to get to concentration. So if we stopped right after these first steps, we would be at moles of iron. So if we want concentration of iron, we need to divide by liters. Sometimes we show this step separately as C equals N over V, right? Do it with a formula. That is also okay. I just did the whole thing using dimensional analysis, and we get our overall answer of 0.075 moles per liter of that iron ion. So the tricky part of these questions doesn't generally tend to be the dimensional analysis part. We've done that lots. It tends to be finding that balanced reaction. So our next question, let's take a look at what we've got there. So we have potassium dichromate solution, and we're analyzing chromium content where chromium 2 ions are being oxidized to chromium 3 ions. So we know we've got oxidation going on one hand. What is being reduced? Well, it's something in this potassium dichromate solution. So remember, the substance that is reduced is high up on our redox reaction chart. And if you look on that redox reaction chart, we see that dichromate's pretty high up there, but only if we add 14 hydrogen ions. But that's okay, because later on in the question we're told this is in acidic solution. So as we were doing before when we were predicting spontaneous reactions, we're trying to take the one that's highest up as possible for that reduction reaction. We're told in this specific question what is being oxidized, but it will be what's lowest down on our oxidation side. So that's the chromium ions. So because this one is in our chart, we can actually use that value from our chart. So the dichromate plus 14 hydrogen plus 6 electrons reaction. And then we can look at our chromium. Well, it's going from +2 to +3, so that's 1 electron. And we want it to be 6, so I'm going to multiply mine by 6. So I kind of did 2 steps at once there, right? Because this would normally be 1 electron, but then I multiplied it by 6 so that our electrons match. Then we can write our balanced equation by taking our 6 electrons and canceling them out and taking everything else. Notice that in this one we have the chromium 3 ions in both products, so they add up to get 8 chromium 3. Again, let's identify which substances we know things about. So we know concentration of that potassium dichromate. We know volume of the titrant, so that's the potassium dichromate again. Notice we end up ignoring the potassium because it's not part of our reaction. We also know 10 milliliters of the sample, and the sample was where our chromium ions were coming from. So we're going to put that under the chromium ions. So again, we've got concentration and volume and volume. Don't use C1V1 equals C2V2. It won't work on this question because we do not have a one-to-one reaction. So we do have enough information about our dichromate, so concentration times volume to get our moles. Then we can use our mole ratio, 1 to 6. Actually 6 to 1 because we got to put the chromium on top. And then again we're looking for concentration, so we can divide by that volume. So concentration times volume to get our moles. Mole ratio, convert to the units that we want. So this one works out to 1.305 before we round it. If we look at our significant figures, we've got 3 here, 3 in both parts of our dichromate, the concentration and the volume. We've got 4 in the volume of the chromium ions, so we want to round that to 3 sig figs. This is one of those rare scenarios where we would get a different answer using the odd-even rule than not, because we end up having exactly 5 following it. So I would accept either 1.31 moles per liter or 1.30 moles per liter, depending on whether you're using our typical rounding or the odd-even rule rounding. Last example that we're going to look at. Again, we need to balance it. So we've got aqueous hydrogen peroxide titrated with sodium perchlorate. So if we look on our table for the highest oxidizing agent, so the thing that is reduced, we're going to see that that perchlorate is going to happen. because again it is in acidic solution. So highest up on our chart, perchlorate. Now the aqueous hydrogen peroxide, might have to look a little harder for that one. So hydrogen peroxide, H2O2. So we're looking down on the right hand side to find that reaction, and it's going to look like this. So we've only got 2 electrons in the oxidation reaction, 8 electrons in the reduction reaction. We need to multiply the oxidation by 4 before we add them up. So that gives us a result where we have 1 perchlorate, 4 peroxide, hydrogen peroxide. On the reactant side, 1 chloride ion, 4 water, and 4 oxygen on our product side. Note that the hydrogen ends up canceling out, so it's actually acting as a catalyst, right? It's not actually taking part in the reaction, in that we don't end up with a different amount of hydrogen at the end than we started out with. So again, this is another one where we have concentration and volume, and another volume when we're looking for concentration. So these are pretty typical how these tend to look on these, because they are being used to analyze substances. So we are looking for things like concentration. The only thing we might be looking at differently is we might be going for a mass of a solid or something rather than concentration. So we end up with concentration times volume gives us our moles, mole ratio to find our unknown substance, divide by volume to get from moles to concentration. When we put that one to the right number of significant figures, 3 sig figs, 0.192 moles per liter. So I did post in those extra questions, some of them were some stoichiometry questions, as well as there being some homework exercises in your textbook. And that takes us to the end of chapter 13.